Ever wondered why oil and water don't mix, yet mayonnaise stays perfectly stable for months? Let's explore the fascinating science of emulsions. At first glance, it seems impossible. Oil and water are supposed to separate immediately, yet mayonnaise, which is mostly oil and water, can sit in your fridge for months without separating. Let's start with the fundamental question. Why don't oil and water mix naturally? Water molecules are polar. They have positive and negative ends that attract each other through hydrogen bonds. Oil molecules are nonpolar with no charged regions. The fundamental principle in chemistry is that like dissolves like. Polar substances dissolve in polar solvents, and nonpolar substances dissolve in nonpolar solvents. The interfacial tension between oil and water is about 50 millinewtons per meter. This high tension creates a strong barrier preventing mixing. Here's an interesting question. What happens when you vigorously shake oil and water together? When shaken, tiny oil droplets temporarily disperse in water, but within minutes they coalesce and separate back into distinct layers due to that interfacial tension. Let's understand the energy dynamics that drive separation. The Gibbs free energy equation tells us whether a process is spontaneous. Delta G equals delta H minus temperature times delta S. For oil and water mixing, we can analyze each term. Delta H is positive because breaking water-water hydrogen bonds costs energy. This is unfavorable. Delta S is positive because mixing increases disorder. This is favorable. For typical values, delta G is approximately plus 44 kilojoules per mole. Since this is positive, separation is thermodynamically favored. This energy barrier diagram shows that mixed oil and water exist at a higher energy state. Nature prefers the lower energy separated state. So how do we overcome this natural tendency to separate? Enter the emulsifier, the molecular hero of mayonnaise. An emulsifier molecule has two parts, a hydrophilic head that loves water and a hydrophobic tail that loves oil. This dual nature is called amphiphilic. In mayonnaise, egg yolk contains lecithin, which acts as the emulsifier. One large egg yolk contains about 1.5 grams of lecithin. Lecithin has the molecular formula C42H84NO8P. Its molecular weight is about 786 grams per mole. Emulsifiers arrange themselves around oil droplets with their hydrophobic tails pointing inward toward the oil and hydrophilic heads pointing outward toward the water. The size of oil droplets is crucial for emulsion stability. Let's calculate why. In a stable emulsion like mayonnaise, oil droplets have a radius of about 1 to 10 micrometers. Here's a key question. Why do smaller droplets create more stable emulsions? Stokes' law gives the settling velocity of a sphere. Velocity equals 2r squared times density difference times g divided by 9 times viscosity. Let's calculate the rising velocity for a 5 micrometer oil droplet in mayonnaise. The radius is 5 times 10 to the minus 6 meters. Oil density is 920 kilograms per cubic meter. Water density is 1,000 kilograms per cubic meter. Mayonnaise viscosity is approximately 5 Pascal seconds, much higher than water. Plugging in these values, we get a velocity of about 4 times 10 to the minus 10 meters per second. How long would it take this droplet to rise just 1 centimeter? Time equals 0.01 meters divided by that velocity, which is about 25 million seconds. That's approximately 290 days. This explains why mayonnaise can last months without separating. There's a minimum amount of emulsifier needed for stability called the critical micelle concentration. For lecithin, the CMC is about 10 to the minus 5 molar. Below this concentration, emulsifier molecules exist individually in solution. Above this concentration, emulsifier molecules spontaneously organize into micelles that can stabilize droplets. A micelle is a spherical structure where emulsifier molecules arrange with hydrophobic tails inside and hydrophilic heads outside. Let's calculate how much emulsifier is needed to coat oil droplets. Consider 100 milliliters of mayonnaise. That's 75% oil by volume. The oil volume is 75 milliliters, which equals 7.5 times 10 to the minus 5 cubic meters. Assume an average droplet radius of 3 micrometers. Volume of one droplet equals 4/3 pi r cubed, which is 1.13 times 10 to the minus 16 cubic meters. Number of droplets equals total oil volume divided by droplet volume, giving 6.6 times 10 to the 11 droplets. Surface area of one droplet equals 4 pi r squared, which is 1.13 times 10 to the minus 10 square meters. Total surface area equals number of droplets times area per droplet, giving approximately 75 square meters. That's astounding! The total oil droplet surface area in 100 milliliters of mayonnaise equals the floor space of a small apartment. Emulsifiers provide more than just a physical barrier. They create electrostatic repulsion between droplets. Lecithin gives oil droplets a negative charge, like charges repel, preventing droplets from coming close enough to coalesce. The electrostatic force follows Coulomb's law. Force equals K times charge 1 times charge 2 divided by distance squared. As droplets approach each other, the repulsive force increases dramatically with the inverse square of distance. The stability of emulsions is explained by DLVO theory, named after Derzhagan, Landau, Verwey, and Overbeek. DLVO theory shows that total interaction energy is the sum of electrostatic repulsion and van der Waals attraction. At small distances, repulsion dominates, creating an energy barrier. Total potential equals repulsion potential plus attraction potential. Repulsion potential is proportional to E to the negative kappa h, where h is separation distance. Attraction potential is proportional to negative A over h, where A is the Hamaker constant. Environmental factors like pH and temperature significantly affect emulsion stability. Here's a practical question. Why does mayonnaise separate and become unusable when frozen? Freezing causes ice crystal formation that physically disrupts the carefully arranged emulsifier molecules around oil droplets. Ice crystals create mechanical disruption that breaks the protective emulsifier layer. Mayonnaise has an optimal pH range of 3.5 to 4.5, typically achieved by adding vinegar or lemon juice. pH equals negative log of hydrogen ion concentration. This graph shows that emulsion stability peaks in the slightly acidic range where lecithin maintains optimal charge. Let's analyze a real mayonnaise recipe from a scientific perspective. A classic mayonnaise recipe uses specific proportions for optimal stability. 1 egg yolk, weighing about 18 grams. 240 milliliters of vegetable oil. 15 milliliters of lemon juice or vinegar for pH control. The oil fraction equals 240 divided by the total volume, which is approximately 0.88 or 88%. This is near the maximum oil fraction that can be stably emulsified, which is about 90%. Each yolk provides about 1.5 grams of lecithin. Surface coverage equals 1.5 grams divided by 75 square meters of droplet surface area, giving 20 milligrams per square meter. This matches the optimal surface coverage needed for long-term stability. Nature's recipe is remarkably precise. Even stable emulsions slowly change through a process called Ostwald ripening. Ostwald ripening occurs when molecules from smaller droplets dissolve and redeposit on larger droplets. Small droplets shrink while large ones grow. The rate equation shows that the cube of average radius increases linearly with time. For mayonnaise stored at 5 degrees Celsius in a refrigerator, the ripening rate is about 10 to the minus 32 cubic meters per second. Time to double the droplet size is about 10 to the 8 seconds, or roughly 3 years. This slow process explains why even well-made mayonnaise eventually separates after many months. Understanding stability helps us understand what breaks an emulsion. Several methods can break an emulsion. Heating reduces viscosity and weakens electrostatic repulsion, allowing droplets to move and coalesce faster. Adding salt screens, electrostatic charges, reducing the repulsive barrier between droplets. The Debye length lambda d shows how salt concentration affects the range of electrostatic interactions. Freezing creates ice crystals that physically disrupt the emulsifier arrangement. Excessive mechanical stress can force droplets to collide with enough energy to overcome the repulsive barrier. Let's summarize the key principles behind emulsion stability. 4 key factors create stable emulsions. small droplet size, low settling velocity, high viscosity, and electrostatic repulsion. Stability is proportional to viscosity divided by density difference times radius squared. Mayonnaise achieves nearly 300-day stability through a perfect combination of factors. Oil droplets of about 5 micrometers in diameter, a viscosity of 5 Pascal seconds, 10,000 times higher than water. Optimal emulsifier coverage at 20 milligrams per square meter. pH control between 3.5 and 4.5 for charge stability. The oil and water paradox is resolved. While these substances naturally repel, clever molecular engineering creates stable coexistence for months. The result is a stable emulsion where oil droplets remain suspended in water indefinitely, protected by their emulsifier shields. This beautiful example shows how understanding nature's principles allows us to create seemingly impossible stable mixtures.